Hi, everyone. Thank you so much for joining us today. Today's webinar by Maria Colgan is co-hosted by the New York Oracle User Group and Viscosity North America, an Oracle partner. My name is Monica Lee. I'm the marketing director for Viscosity. We are a full Oracle stack consulting firm. Sorry, I can't talk today. And our core expertise is in Oracle database, and that includes things like RAC, Oracle Apex, zero downtime migrations, performance tuning, and high availability. During today's presentation, feel free to submit questions to Maria in the control panel that you see. She'll get to them when she can, time allowing at the end, and she's even got some of your questions from part 1 that she's going to try to get to today as well. Representing the New York Oracle User Group today is NYOUG President Coleman Leviter. So I'm going to pass it over to him, and he's going to introduce you to NYOUG.
Thank you, Monica. So welcome everybody to this webinar series we've been co-hosting with Viscosity, and just want to welcome you to all these great technical presentations that we have today. As far as New York Oracle Users Group is concerned, we was formed in 1984 for the exchange of ideas and support among users of the Oracle products. Connect with us on Twitter, Meetup, LinkedIn, Facebook, and our website, nyoug.org, where we also have the presentations and the videos for some of the presentations. Also reach out to the membership through the community.oracle.com user group community. Just look on Oracle's website and you'll see everything with the regional groups and what activities are going on. And thank you, Viscosity North America, for co-hosting Maria. Maria Colgan is a master product manager at Oracle Corporation, has been with the company since version 7.3 was released in 1996. Maria's core responsibility is to advocate for the Oracle database and the best practices for incorporating it into your environments. She's also responsible for getting the feedback from our customers and in partners incorporate into future releases of the product. Prior to this role, she was a product manager for Oracle Database In-Memory and Oracle Database Query Optimizer. Thank you again. I'd like to turn over to Maria, who's going to give part 2 of the explain plan.
Thanks so much, Coleman and Monica, for that great introduction. We do have a huge amount to cover this morning, so I am going to jump in and get started. So in part 1, we covered what is an execution plan, how to generate one, and we looked at the first 2 parts of the plan table itself, or the plan operations themselves. We looked at cardinality estimates, and we looked at access methods. In part 2 this morning, what we're going to look at is joins, the join order, and then we'll look at plans with partitioning and with parallel execution before we wrap up by looking at an example, and I'll explain to you the kind of questions you should ask when you're given one of these plans to determine if it really is a good query. But before we jump into that, I want to make sure that we address some of the questions that came up last week. So the first question I got was, is the cost value of the explain plan worth looking at? And it is a column that we didn't really touch on inside in the plan. So what is the cost? Well, it is the representation of the amount of work or resources needed to complete that query. So the final cost for the query, that's what it is, how much work or resources are going to be needed to process that query. And the optimizer uses things like CPU and IO in order to determine that work or those resources. And it estimates how much CPU and IO is needed for each of the operations in that plan. It is an accumulative total as you go up through the plan. But what you notice is the math is not always exactly as you expect, and that's because there's often hidden costs that get put in, things like the CPU overhead of applying a filter predicate after we've done the IO for that SQL statement. So it's not one of those things that I strongly recommend you try and reverse engineer or fully understand. The purpose of the cost in the plan is for comparative reasons. So if I've got two execution plans, the one with the lower cost is supposed to be the more efficient of the two plans, the one that will use less CPU, less IO. That's the point of it. So I wouldn't spend a huge amount of time on it, but it can be useful if I'm comparing two plans. Oftentimes, I'll have a plan I think the optimizer was going to go with, and what I get is something different. And when I force my plan, I realize the cost of my plan is actually a lot more than the cost of the plan the optimizer came up with. And chances are the plan it came up with was more efficient. So cost was a popular topic last week. I got asked, how do we calculate the cost? Again, this is something I deliberately don't include in the presentation because, to be honest with you, you can't change it. Although you can influence it a little bit with parameter settings and with statistics, but generally I don't share these calculations. But for the person who asked, I do have them here. As I've said, a lot of these stats are reliant on init.r parameter values, for example, multi-block read count, the index cost adjustment parameters, things like that. Parameters that I don't like to talk about because I don't like people to change them. You should be aiming to go with the default value for all of those parameters. Why? That's the value that Oracle does all of its testing and verification of new transformations, new adjustments to the cost model is always done with the default value for those parameters. And so if you're changing it, then chances are you'll get unexpected behavior and you'll end up having to do a lot of work to kind of unpick those changes. So for me, I'm sharing them because you asked for them, not because I think you need to know them. That's why they weren't in the presentation, but they are the formulas. I also put a link into another presentation where it lists a lot more of the formulas. Okay. Another one of the questions from last week was we talked about the fact that when you're viewing a plan or producing a plan, you can use explain plan, or you can go against $SQL plan, that internal view, to see the actual plan that was used during the execution of the SQL statement. So the question came in and said, can I actually see the results of $SQL plan, like the actual plan in the cursor cache with SQL Developer? And if you're used to SQL Developer, you'll know that it offers you auto trace and it also offers you explain plan as little icons above the worksheet. What you may not realize is it will also show you the plans from $SQL plan. If you click on the little drop down arrow menu next to the explain plan command, it will actually show you that, yes, I found this SQL statement in the cursor cache, and here's the actual plan from $SQL plan. So yes, you can see the plan in $SQL plan with SQL Developer. More info on SQL Developer, definitely go to thatjeffsmith.com. He has a phenomenal blog with everything you may ever want to know about SQL Developer. So definitely, if you are using SQL Developer, make sure you're going to thatjeffsmith.com for information. So I thought these two questions were a great lead into what we're going to do this morning, because it asked to cover nested loops and hash joins and parallel plans. So with that, let's jump in and get started, and we'll talk about join methods first. So last week we mentioned the fact that Oracle offers 9 different access methods. How many join methods do you think we have? Well, it turns out we have 3. Now, there are a lot more join types that we'll talk about in a moment, but there's really only 3 join methods Oracle uses: nested loops, hash join, and sort merge join. With nested loops, this join method is usually chosen when the tables we're joining are quite small, and you can think of it as embedded for loops. For every row in the outer table, we're going to scan the inner table looking to find a match. And as I said, it's normally chosen when we've got 2 small tables that we're doing joins, and we have an effective way to look up rows or matches in that inner table. So in other words, normally it's an index access on that inner table. A hash join is done when the objects are larger and we have an equality predicate. With a hash join, what happens is we scan the smaller of the 2 tables first, we apply any where clause predicates we may have for that, and then we apply a hash function to the resulting rows, to the join column of the resulting rows, and we build a hash table in memory. We then go and scan the larger of the two tables, which will be the second one. Again, we'll apply any where clause predicates we have to that. And then the same hashing function is applied to the join column of the second table. And then we do a lookup in the hash table to see whether or not we have a match. The third and final option is a sort merge join. A sort merge join is done when one or both of the inputs into the join is already sorted on the join column. So typically that happens if we've got an index that's got the join columns as the leading edge of it. So how it works is we'll actually sort both of the inputs on the join key, and then we merge the two lists together to complete the join. So it's a two-step process, and as I said, it's typically chosen when at least one, if not both of the inputs are already sorted on those join columns, and that's typically because they're the leading edge of an index. Now, so 3 join methods, but there are 5 join types. So your traditional query, your traditional, empt and depth style query uses an inner join, one where we only return the rows where there's an actual join between the two tables. It's kind of the most common type of join you get in a query. You then have the option to do outer joins. With an outer join, we not only return the rows where the condition is met, where the join actually returns rows, we also return rows from one or other of the tables in that join, or if you do a full outer join, all of the other rows from the other two tables. So let me step back and talk about it for a second. So if I'm doing a left outer join, what it means is I'm going to return all the joins that meet the join condition, but I'm also going to return all of the rows from the left-hand side, even though they didn't have a match. So match everything, and then all the other rows from the left-hand side where there isn't a match. The reverse is true for a right outer join. So return all the rows where there is a match, and then all of the rows, all the other rows from the right-hand side of the join, even though there isn't a match. And then a full outer join is return all of the rows from both tables, even if there isn't a match, as well as the matched set. Very similar to a Cartesian product, one where we join all the rows from one table to all the rows in the other table. Cartesian product is typically only chosen if the objects are very tiny. So we assume only one row or no rows potentially for those objects. So if I've got stale or missing statistics, Cartesian products can pop up because the optimizer thinks there's not going to be any rows, when in fact there are actually a lot of rows because I misled the optimizer with bad stats. It's also chosen if I forget the join condition. So if I'm writing a complex SQL statement and I'm joining lots of tables together, if I forget the join condition between two tables, then the optimizer has no choice but to pick a Cartesian product, because it has to join all of the rows from one table to all of the rows in the other table, because we haven't told it any other thing to do. The last two, semi-join and anti-joins, are seen if we've got subqueries in our query. So in other words, we are filtering out rows from the outer table by applying some kind of logic in these subqueries. So for example, they can be an exists or an in subquery, then that's a semi-join. And what it means is only return rows from the outer table where we have a match with this subquery. So this exists or in subquery. An anti-join is the opposite of that. It happens when the subquery is a not exists or a not in. And again, it's basically return all the rows from the outer table except for the ones that have a match with this subquery. So there are 3 join methods, 5 join types. Now that you have that information, I want you to actually take a look at this plan and tell me, where do you see the join information being shown? Well, it's shown there in the operations column. Okay, hopefully you guys can still hear me, because I'm having trouble now being able to progress my slides.
We can still hear you.
Oh, good. Okay. So I don't know why I can't. Oh, there we go. All right. So I don't know what happened there, but let me go back because we've missed a couple of slides. Oh, and I'm going to show you all the answers now. All right. So what I wanted you guys to do now that you've seen the answers is play a little quiz with me. What I was hoping to do is we're going to be the optimizer. Here's your first query. The query is a join between employees and the department table. We've got a where clause predicate on the department table, and we've got a join predicate between employees and department on the department ID. Now, these tables are small. The employees table has 107 rows, department's 127, and there is, as I said, foreign key, primary key relationship on that department ID. Now, if you were watching closely as I was flicking through the slides, you already know the answer. The answer to this one is the optimizer chooses a nested loops join. Why? Because I've got that easy access path to be able to look up the information inside in the table on the right-hand side, we went with the for loop. Now, starting in 11G, you'll notice that the nested loops plan often show the nested loop operator twice. And I wanted to just spend a second talking about that. The reason we show it twice is that we changed the implementation of a nested loop join in 11G. And what we did was we initially did the lookup of the index. So the join between the outer table and the index lookup is done in the first operator. And then the second nested loop operator is actually batching up the row IDs that come out of that index access so that we can minimize the number of IOs or single block reads we do, retrieving the corresponding row from the employees table in this case, or sorry, from the departments table in this case. So that probe, although we probe each go round, we don't actually go and get the corresponding block from the inner table until we've batched a number of those row IDs, and then and only then do we make the request to the employees table. The goal or the premise of this is that if we batch up those row IDs, chances are we can get multiple rows from a single block. And so if we did it the old-fashioned way, we would reread that block multiple times, and this way we only read it once. So that's why you see the two nested loops often in plans now. If you've migrated to 11G, 12C, 18, or 19, you may see that plan change. What about this one? I'm joining orders to order items. I have an equality predicate. The tables are larger now, 105 rows for orders, 665 rows for order items. I'm fairly certain you would have been an easy guess for you. It's a hash join. Why? We have an equality predicate. I didn't mention anything about indexes, and so a hash join would be the most efficient way to process those two tables. All right, here's your last one, sales and customers. I've got an equality predicate between these two tables on customer ID. The sales table has just shy of 1,000 rows, while the customers table has 55,500 rows. And I do have some indexes. So I have a primary key index on the customer ID in the customer table and a foreign key index created on that customer ID in the sales table. So although I've got large tables, I have that efficient access method. Does the optimizer pick a nested loops, or does it pick a hash join? Well, turns out in this case, it picks neither. There was actually no need to do the join at all. Why? Because we never selected any of the columns from the customer table in our select list. You'll see there, all I took was one column from sales. And because I had the primary key, foreign key relationship defined, I had those constraints in place. The optimizer was able to happily remove the customer table from this query. We call it table elimination. And the reason we're able to do it, as I said, is that primary key, foreign key relationship is defined, which means there is no customer ID in the sales table that doesn't have a match in the customers table. So therefore, I can just access the sales table, return the sales quantities, and never bother doing the join. That's one of the #1 reasons I tell people, if you know information about the relationship between the data in your tables, always share it with the optimizer, because it can do something very clever like what I've just shown you there. So that's great. You told me I've got all these different join methods and join types, Maria, but what if I think the one I've got is wrong? So let's say it assumes nested loops is being selected instead of a hash join. Typically that's done when you've got a cardinality misestimate on the left-hand side. So the first table that we're accessing, if we think the number of rows coming out of that table is a small number of rows, then we would choose nested loops by default. However, if for some reason, and this goes back to what we talked about last week, if the cardinality estimate is incorrect, because maybe we've got a function wrapped column, maybe we're using multiple predicates on that table and they've got a correlation between them, or I simply am missing or have stale statistics, they can all be reasons why a nested loops is chosen instead of a hash join. A hash join is chosen instead of a nested loops is less common, but it still does happen. And it often happens if the rows coming out of the left-hand side of the join are actually clustered. In other words, they're in some sort of ordered fashion that I could perhaps get them out of an index in that ordered fashion. And so the number of IOs needed to read that data is actually far less than the optimizer estimates. And so that can cause us to pick a hash join instead of a nested loops. There isn't a massive way to fix the second one. The first one, obviously, you fix the stats issue and you get it. The second one, letting Oracle know about the clustering, is much, much harder. And so the good news is, starting in 12C, we introduced something called adaptive plans, and adaptive joins methods will actually fix or help this scenario. So let me explain how that works. Let's say we're doing a two-table join between order items and product information, because I'm trying to find all of the products that has a unit price of 15 and where we've sold more than one of them. Now, I have a join predicate, so I don't need a Cartesian product, so that's there. It's an equality predicate, so I could go with either a nested loops or a hash join. With adaptive plans, what actually happens is we'll compute both subplans, or both options. It could be a nested loops where we would scan the order items table and then use an index to probe into the product information table, or it could be a full scan of order items and then a full scan of product information and hash join them together. So both plans are computed and are stored in the cursor just in case. And then what you see is a new operator is inserted into that plan. It's called a stats collector. And what it's going to do is it's going to buffer the rows that flow out of the left-hand side, and it's going to prevent them from moving up in the rest of the plan until we see roughly how many rows are coming out. So in other words, this stats collector is put in place to buffer the rows so we can monitor what's going on. And if the number of rows that's produced by the left-hand side is less than a threshold, we go with the default plan, which in this case is nested loops. But if the number of rows we're seeing coming out of the left-hand side goes over that threshold, then we'll instantly flip to the hash join. This decision, so as I said, once the rows are buffered until that final decision is made, once the decision is made, the stats collector becomes a no-op. In other words, all subsequent executions will use the final plan that we decide. What the thresholds are, in my example, I said it was 100. That's not a hard-coded value. It can be, it is very dependent, on your particular queries, what that threshold is, or that tipping point is between a nested loops and a hash join. And vice versa, by the way. I can start with a hash join and flip to a nested loops, or I can go the other way. I can go nested loops to hash join. But once the decision is made on the initial execution, then I will use the final plan for all subsequent executions, and that stats collector and the other operators are no-ops or invalid. So if I ask Oracle with adaptive plans, if I do an explain plan command for that, I will get that default plan. I get no mention of the fact that it's an adaptive plan. So just be a bit careful of this. At the very beginning of the session last week, I asked, in what occasions would an explain plan command not actually show you the final plan that was used? And when we talked about that, we talked a lot about bind peaking, but adaptive plans is another example where the explain plan command may not show me the actual plan used. If I use $SQL plan to show me the plan, it doesn't tell me it was adaptive either by default. What it tells me is what the final plan used for that SQL statement is. So in my example, it shows me a hash join. If I want details about adaptive plans, then I'm going to take advantage of the format parameter on DBMS display or DBMS XPlan display cursor. I can add additional parameters to the format. Remember, that's a super powerful parameter at your disposal that shows you a lot more information about your execution plan. I can add 2 new parameters to that. I can add plus all dynamic plan. And what that'll do is it'll show me all of those operators in the plan, the choice between the different join methods, the statistics collection, as well as the different access methods to the table on the right-hand side. So in this case, the index lookup as well as the full table scan. And if I also add plus adaptive, it'll give me information at the bottom of the plan on the kind of notes section telling me which of those operators is used or disabled so that you can follow along with the decision. Now, as I said, they become null and void steps in the plan, so there's no overhead other than on the very initial execution where we're looking to make that correct estimate. So now that we've talked about joins, I want to move on and talk a little bit about the join order, because we also want to talk about partitioning and parallel execution. So the join order, of course, is the order in which the tables are joined together in a multi-table statement. So in other words, if I'm joining table A to B to C, we need to figure out what's the most efficient way to join all of these tables together. And the optimizer has one strong goal when it's trying to define the join order. It's looking to minimize the number of rows or the amount of data it needs to carry around between each of these joins. So in other words, it's trying to create a join order that will eliminate as many rows as possible, as fast as possible in our execution plan. And the join order is also strongly affected by the access methods that we have into the different tables. So for example, if I'm trying to force a particular join order among tables, like in a transaction processing system where I'm going to be doing a bunch of nested loops, if I create the indexes on the tables that I want to be on the right-hand side of those nested loops, if I create them with the join column as the leading edge of that index, I may be able to kind of encourage the optimizer to pick a specific join order, because I'll have a very efficient way to do the right-hand side of each of those joins. Now, regardless of what kind of index creation strategy I may have, the optimizer does have some hard and fast rules that it's going to follow when defining the join order. So for example, if there is a join in my multi-table query where it's guaranteed to return at most 1 row, then that join always goes first. So what kind of join would that be? Well, if it's a join between 2 primary keys, or if it's a join between 2 unique scans, index scans, then if 1 row is coming from one of the tables, I can at most find 1 match, or therefore return 1 row, or I find no matches. So if I'm doing, you know, an unique scan or a primary key lookup on that inner one, and I only have 1 row to probe in, then at most only 1 row would come out, and so that join goes first. The join order is also being dictated by your query if you use outer joins. If you use outer joins, then the table with the outer join operator must come after the other table in the join, so we're able to pick up all of the rows that don't match as well as the matching rows. So you are dictating to a certain degree the join order when you use outer joins. The same is true with views. So by default, if your query has a view in it or accesses a view in it, Oracle will try and do something called view merging, where we take the definition of your view, we insert it into the SQL statement, and then we try and optimize it as a whole. That way, looking at all the possible join orders between the tables that weren't in the view and those in the view. But if for some reason we can't do that view merging, perhaps because you supply a no merge hint or because of just the way the query is written, then what happens is we need to build the view, the final result of that view first. So join all the tables in the view first, and then join that result set to the remaining tables in your query. So just bear in mind that views can also kind of dictate the join order that we may use. When it comes to being able to identify the join order in the actual execution plan, I've heard a number of different kind of tips on how to do this, but one of the things I discovered as I've done it is that there is no hard and fast rule because of some of these transformations the optimizer gets up to. And if you're not familiar with that concept, what a transformation is when the optimizer tries to rewrite your query in a semantically equivalent. So in other words, it's going to return the same result, but we've written the query in a different way in order to be able to open up additional access methods, join methods, or even join orders. And so all of the rules I've ever heard about the join order have never stuck 100% for all plans. But I'll give you the most basic one first, and then I'll show you the trick I use to always make sure I've got the join order correct. So if I'm looking at an execution plan, and a simple enough one like the one we've got before you, this rule normally obeys. I start at the top and I work my way through the operations in the plan until I find the first operation that produces rows without consuming any rows. Remember, each operation in the plan either produces or consumes rows or does both, all right? And so if I look at my plan here, if I start at the top at line 0 and I work my way down, the first operation in that plan that produces rows without consuming any rows is the table access full on department. So now I know that's the first step. And remember, it is a tree, so I need to walk back up the tree to the next step from that table access full. And so I need to then walk up to the next branch and walk down the other side. In this case, that takes me to employees, and then that joins to employees again, and then we go to department, and then we go to jobs. So that's how this particular plan works. But I'm going to show you a trick that is good for any SQL statement because it'll always show you the proper join order without having to try and navigate, how far into the plan this step is, and then having to try and work out what the corresponding next node up in the tree is, and so on. So how do I do it? Well, when I ask Oracle to display the plan for me, I also ask it to display the full outline of the plan. So the outline is a full set of hints that can be used to reproduce that exact plan. And one of those hints is called the leading hint. And what that does is it defines the join order of the tables in that query. And so the leading hint, although it uses the table aliases and not the full table name, so be careful with the aliases you use, and it gives me also the query block names. If you're not familiar with that, have a quick Google. You should find a blog post about what query block names are. There should be one on mine, and Jonathan Lewis has a number of blog posts about that too. But what it shows you is the join order. So in this case, departments to employees, to jobs, to departments. So this is not the same outline for the plan we just looked at. This is the outline for the tuned plan, but you at least get the idea of what I was able to do. So what if I get the wrong join order? I don't think it's joining the tables in the order I want them to do it. Again, it goes back to what we talked about last time. Single table cardinality estimates are very, very important. If we think the number of rows being returned by the access to that table is far less than it really is, that can really impact the join order. Because remember, we're trying to eliminate or minimize the number of rows we're carrying around. If our cardinality estimate is wrong and we start on a table that we think is small but turns out to be very large, that can be a problem. The same is true with join cardinality. So when we are doing joins and we're doing multiple column joins, especially, in other words, I'm using multiple columns to join table A to table B, Oracle assumes each additional join predicate you're specifying will reduce the number of rows being returned by that join. If that's not the case, if, for example, we know we're joining on city and state, so city equal, city are equal to the columns, sorry, the city column on both tables have an equality predicate between them, and the state column on both tables has an equality predicate on it. The optimizer is going to assume that combination of city and state will actually reduce the volume of rows more so than if I just did city and city. But most of the time, city and state is a unique combination. And so the addition of the state predicate doesn't actually reduce the rows, and the optimizer will misestimate the number of rows being returned by that join. So make sure you're using your extended statistics to tell the optimizer about that type of correlation, and your single table estimates are correct. Okay, so let's move on now and talk about how to read plans where one or more of the objects in that plan is using partitioning. Now, if you're not familiar with partitioning, what it is a way to break up a large table into smaller, more manageable components. But what's great about partitioning is it's completely transparent to your application code. So your application code doesn't need to know that we have partitioned the underlying table. But by dividing it up into these smaller pieces or physical objects called partitions, it makes it easier for us to manage, and potentially it can improve the performance of our queries because we can do something called partition pruning. In other words, we can access only the partitions we need to answer that query and ignore all the other partitions in the table because they're not relevant or they don't hold any relevant information for our particular query. So basically the fastest IO you do is the IO you don't do. In other words, if I don't need to read that data, then I can actually speed up my query. So how does it work? Well, if we end up with a where clause predicate on the partitioned column, then we can get this partition pruning. So in this example, I'm looking for all of the sales we made in the weekend of February 10th through 12th, 2020. So in other words, Friday, Saturday, and Sunday of that weekend, what sales did we make? My sales table is partitioned by day, and so I'm only going to access the 3 relevant partitions for that query, the 10th, the 11th, and the 12th. I'll scan those where clause predicate, or sorry, those partitions. I'll sum up the sales amount and I'll return it to the end user. All the other partitions in the table are automatically pruned out or skipped because I don't need to access them. So when it comes to doing this type of pruning of partitions, we can do it in one of 2 ways. The example I showed you here is something we call static pruning. In other words, the optimizer knew which partitions it was going to hit when it parsed the SQL statement. Why? Because we had the where clause predicate directly specified on the partitioning key. Sometimes, however, it's dynamic pruning that's going to happen. In other words, the optimizer knows or suspects that we're going to prune out some of the partitions in the table because I have a join predicate on the partition key, but it doesn't know what the actual partitions are that we're pruning out until execution time, because it has to wait for the join to complete to tell us which partitions we're going to hit. So we call that dynamic pruning. And so we can see based on the execution plan whether we got static or dynamic pruning with partitioning. So first of all, how do I identify partition pruning is taking place in my plan? Well, when you've got partitioned objects, 2 additional columns will appear in the execution plan table, P start and P stop, which indicate the partition numbers that we are touching from those particular objects. You'll also see above the table access, you typically see how we're accessing those partitions as well, whether it's index range or a hash partition too. So you normally see something in the operations column, but really P start and P stop are the true indicators that you are accessing a partition table. If you don't see numbers in those columns, but you actually see the word key appear in the P start and P stop, what it means is we believe we're going to get pruning, but it's not static pruning, but dynamic pruning, because I'm waiting on the join key to tell me which partitions we're going to access. And that's why you see the word key in P start and P stop. So if we look, kind of zoom in and we look at a much simpler query, and we're asking, or we look at the P start and the P stop for this column. So I'm accessing a table called RHP tab. So I'm accessing a large table. I have two where clause predicates, one on the customer ID and one on the time ID column. And if I look at the table, so you see there what I was talking about in the plan, line 2 and line 3 of that execution plan, you can see the partition range single and partition hash single operators in there. That's giving me information about which partitions we're hitting in the table, but P start and P stop will show me the actual partitions that are being hit. And if I look, I see a lot of numbers in that P start and P stop, so I want to explain what those numbers all mean. If you didn't already guess it from the extra partition operators in the plan, my table is ranged partitioned on the time or date column, but it's also sub-partitioned by hash. In other words, each partition is broken up again into sub-partitions. And in this case, I have 2 of those. So here, what I'm saying is that my table is first broken up by date, and I have 1 to n partitions. And in my example, n is equal to 10. So they're the partitions in the table. And then within each of those partitions, I have sub-partitioned them again, or broken them up again, in this case with just 2 sub-partitions. And so when it comes to numbering the partitions, we have the partition numbers, which you see there, 1 through 10, the sub-partition numbers within each partition, which is 1 and 2, and then we give every physical object inside of the partition table its own number. So that number is between 1 and n times m. So in my case, that's 1 through 20, because each of the objects in that plan will, in that table will have its own unique identifier, 1 through 20 in this example. So if we go back to the execution plan, you'll see 3 sets of numbers in the P start and P stop column. And what they represent is the overall partition number. So it's overall partition 10. And that partition appears in range partition 5 of my table. And the sub-partition within that is partition 2. Okay. Again, do I really need to understand all of this? No, you're getting partition pruning. That's great. So the first thing to take away from this is, am I getting partition pruning? I am. That's a good thing. I'm going to get the performance boost. But knowing exactly which partitions are being touched is what I'm explaining to you now. That's the extra information you can get from the P start and P stop columns by looking at these different partition numbers that are being highlighted there in the P start and P stop column. And how do I know which one is range and which one is hash? If I look across, it tells me on line 2 of that plan, partition range single. So a single partition, range partition is being selected. That's partition 5. Line 3 tells me partition hash single. So a single hash subpartition is being selected. In this case, that's subpartition 2 of range partition 5, which has an overall partition number of 10. So hopefully that's starting to make some sense to you. That's static pruning, where I actually get the numbers. So I want to spend a little bit of time now talking about dynamic pruning, when I actually get my pruning via a join. And here, what I'll get in my P start and P stop column is the word key, because I don't actually know which partitions are going to be pruned. I'm going to get that information via a join. And this is a great example, because typically, especially if I'm doing star schema style data warehousing analytical query, chances are I have partitioned my main fact table, in this case, the sales table, but the where clause predicate has come in on the time table or the time dimension, which is not partitioned. But because there is an equality predicate between the time dimension and the sales table, I'll be able to do the pruning via the join. So even though I have a where clause predicate, this time the sales table is partitioned by month, I have a where clause predicate that's coming in on saying where the month is either January, February, or March. And so I can do dynamic pruning by using that join column to determine the join key or which partitions to access. So again, I'll only access 3 partitions and I'll get that information via the join. So when I look at the execution plan for that SQL statement, you'll see I don't know what the partitions are because I don't know at parse time, but at execution time, I will get some partition pruning via that join. So the other thing you're going to see in our extended plan, where do I identify this partition pruning is going on? Remember, you're looking at the P start and the P stop columns. That'll show you what partitions are being accessed. I talked about the fact that if you see numbers, then you're getting static pruning. If you see the word key, then you're getting dynamic pruning. But in my example here, I'm getting something else. I'm getting something that's called BF0000. What is that? Well, that indicates bloom filter pruning, or bloom pruning is occurring in our SQL statement. So what does that mean? Bloom pruning is a great performance enhancement that Oracle has implemented, where when we're doing a hash join between tables, we can create something called a bloom filter that's passed to the table on the right-hand side as part of that scan of that table. We'll tell it, these are the partitions you need to access. So in the example, what I was doing was I was joining the accounts table to the transactions table. And because it was being done through a hash join, bloom pruning was being used in that SQL statement. So what happens is we're going to start by scanning the smaller of the 2 tables first. So in this case, that's the accounts table. We'll apply any where clause predicates we have to that table. And as we create the hash join in memory from the results of that scan, we're also going to create a bloom filter in memory. Okay, now I've managed to delay or see a delay again in my slide progression. So there we go. All right, so as I said, as those rows flow out of the accounts table to begin the hash join and to build the hash join in memory, it will also create this bloom pruning list. And what that is it builds a bit vector, which is a very, very small array that has zeros and ones. And any position where there's a 1, then that's a partition we need to scan. If the position is a 0, then we can skip that partition. So when we pass that down to the scan of the transaction table, we look up each partition in that bit vector and we say, based on the join condition, we either need to access this partition or we don't. And for the ones where we don't, we can simply skip it. So when we scan that fact table, only the partitions where we have a 1 in the bit vector are going to be scanned. And then we apply any additional where clause predicates we've got, and only the results of that get returned to the hash join. So the volume of data coming into the hash join is going to be far less because we were able to take advantage of this Bloom pruning or Bloom filter as part of that join. So it makes it very efficient for parallel plans to get additional partition pruning through a join or through dynamic pruning. Okay, so I know we're starting to run out of time, but I did really want to spend some time looking at parallel execution inside in our plans, because it really does extend the number of operations in a plan, making it feel much more complex. But once you understand it, I promise you, it won't seem nearly as complicated. So just to make sure we all understand what parallel execution is, when you connect to the Oracle database, we create a background process for your session. And if you run queries serially, in other words, you never take advantage of parallel execution, it is that process that is doing the work, doing the IO, processing the data, filtering it out, joining, aggregation. It's all done by your session. But if you connect and then you start to use parallel execution, then your background process or your session process actually becomes something called the query coordinator. And it actually doesn't do an awful lot of the work for your SQL statements. What it'll do is it'll actually go and get parallel server processes from a pool of shared resources inside the Oracle database, and it will then tell those parallel server processes what work they need to do. So it divides up the work between the parallel server processes. They go ahead and execute the query. They communicate with each other and with that query coordinator via in-memory buffers that typically come out of the large pool or the shared pool, depending on how your memory's been allocated. But once they've finished processing as much of the query as they can, they send their results to the coordinator, who normally just aggregates up those results and returns them to the end user. And all of this, the distribution of work to the parallel server processes, the communication between those parallel server processes with each other and with the coordinator, all of those steps are shown in the plan, which is why a parallel plan can look a little bit more complicated than you'd expect. So here I'm just joining the sales to the customers table, but you suddenly see, because I'm using parallel execution, a whole bunch of additional steps in that plan that can appear initially as very complicated. But there's a couple of rules that you can use to try and process these types of plans. First and foremost, the query coordinator always writes its name in the plan. So in this plan, we see the query coordinator is there on line 1 of the plan. All the operations above that entry in the plan are typically conducted by the query coordinator. In this case, all the coordinator is going to do is return the results to the end user. It doesn't actually do any of the work in the plan. And actually that is the ideal situation, because it means there's no serial point or serial execution in our statement. It's all being done in parallel. So that's actually a good thing. All of the operations that happen below step 1 in the plan are actually being conducted by the parallel server processes. In other words, the majority of the work has been done by the parallel server processes. So that's the initial breakdown of what happens, what did the coordinator do, and what did the parallel server processes do. But I want to now look inside the second part of the plan, what the parallel server processes did, and explain that to you. So first things first, when the parallel server processes are asked to do work, especially when they're reading the base objects, we need to divide that work up among the parallel server processes. And what we say is that we divide the work into granules, so units of work for these parallel server processes. And we do that in two ways. We can either give each parallel server process its own partition to work on. Now that may be a subpartition or a regular range partition or hash partition, whatever it may be. Or we give them a range of database blocks to work on. So for example, objects that are not partitioned, we simply divide them up into these ranges of database blocks. Each parallel server process gets one granule to work on. They work on that granule, they return the results, and when they do, they either stop because there's no more work to do on that operation, or If there are additional granules still available because we haven't finished the whole scan, then they'll pick up another granule and they'll continue to work on that until all the granules or units of work have been done. So the first thing you see, and it's normally right above table access, is you'll see how we've divided up the work. So in this case, in the plan that I'm showing you there, you'll see both the sales table and the customer table. They're not partitioned. And so the unit of work or the granules we used were blocks. How do I know? Well, it says PX block iterator. In other words, the parallel server processes are iterating over this table by reading chunks or ranges of blocks until we've read all of the data. If it was a partition access, then you would see PX partition range all. In other words, I'm going to read all of the range partitions for the sales table in parallel. So each parallel server process would get a different range partition from the sales table. They'll scan that table, apply any where clause predicates they may have. Once they finish that scan, they return the results, and if there's additional range partitions that needed to be scanned, they would move on to the next one in the list and so on. So they keep working through them until all of the operations have been completed. Now, how do we break up the different access paths? So we looked at full table scan, which can be a block iterator or a partition iterator. But some of the others, we can only parallelize those operations if the object is partitioned. So last week when we talked about parallelizing operations, I mentioned a lot of the index access paths by default can't be parallelized. So index range scan, index skip scan, those types of accesses typically are not parallelized unless the underlying object is partitioned, in which case then we can take advantage of parallel execution because each parallel server process will get a different partition in that object. So just bear that in mind when you sometimes see, am I getting parallel, am I not? So that's how we divide up how we access it. But oftentimes we'll actually use multiple sets of parallel server processes to do different work inside in the query. And you often see this when you've got a multi-step execution plan. So if I've got a very simple SQL statement, select a column from a table where, and it's just one table query, very simple where clause predicates, I'll have one set of parallel server processes. But as soon as I do something like a join or an aggregation or a group by or a sort or something like that in the query, oftentimes I'll actually get two sets of parallel server processes. We call these the producers and the consumers, and they have different roles in the plan. And what you'll end up seeing in these execution plans is actually the communication back and forth between these parallel server process sets. So here's how it works. Let's imagine we're doing a two-table join between sales and customer. We start scanning the customer table because it's the smaller of the two tables first. And the producers, the parallel server processes 5, 6, 7, and 8 will break up the rows inside the customer table. They'll process their independent granules and they'll apply any where clause predicate there is for the customer table. In this case, there isn't one, and they send the results to the other group of parallel server processes that we call the consumers, who will catch those rows. Now, because there's no join rows to continue the next step, which is the hash join in the plan, the consumers simply catch the rows. Once the producers finish scanning the customers table, they'll switch over and they'll start scanning the sales table. And again, apply any where clause predicates they may have and start streaming rows to the consumers. Now the consumers have all the rows from the customers table, and now they'll be getting rows from the sales table. They can begin that join, which they will do, and they will then start sending the results of that join to the query coordinator that'll aggregate them up and return them to the end user. So along with the query coordinator, you may actually get 2 or more sets of parallel server processes executing that query And in this case, even though the parallel degree was 4, there were actually 8 parallel server processes helping to execute that query. And you can see all of this communication back and forth, steps being done by the consumers and the producers inside in the plan. Again, it's one of the reasons why it looks a little more complicated, because not only do you see how the parallel server processes are breaking up the work among each other, but you also see how they're communicating between the different groups in the plan. So if we look back at the plan we were for our sales and customers, what we'll see there in blue are the steps that the operator or the producers are doing. The steps in pink are what the consumers are doing. So you see there the full table scan of the customers table. You see we broke the customer table up into ranges of database blocks. That's how the parallel server processes divided the work. And once they completed that scan, they used a hash distribution to send those resulting rows to the consumers. And you see there line 8, the consumers simply cut line 4, the consumers simply cut the result and they didn't do anything with it. Then the producers went over and they scanned the sales table. Again, they broke up the sales table into blocks of or ranges of blocks. That's what you see on line 10. Once they had scanned the sales table, they sent the results to the consumers. That's what they're doing on line 9. And then on line 8, you see the consumers catch those rows and begin to do the hash join on step 3 of the plan. Once they completed the hash join, they sent the results to the query coordinator. That's what you see on line 2. The query coordinator caught those results on line 1 of the plan, and on line 0 returned the results to the end user. So I know it can seem complicated, but once you understand the flow of parallel execution, it's actually quite clear what's going on in the plan. Information about parallel execution also shows up in other columns, not just in the operations column as we were looking at it. You can see the producers and the consumers, or the different parallel the different parallel consumer groups, so to speak, or the different groups of, or sets of parallel servers being shown in the TQ column. You will also see information about how the parallel server processes are distributing data or sharing data between the producers and the consumers inside in the plan. Now, I'm going to skip forward, but I am going to share all of these slides with you where I explain how we do each one of these distribution methods. I'll share all of this, but I am very conscious that I've already used an hour of your time, and I'm sure you're very, very busy. But again, the PQ distribution column shows you that information. I talk a little bit about the fact that we now offer hybrid distribution methods as well. And we also have one last column in the execution plan that is for parallel execution. It's called in and out. And what it basically controls is whether or not the different steps in the plan are happening in parallel, if they are going serial, or if we're able to combine multiple steps in the plan. In other words, are we using producers and consumers so that the next step in the plan can actually be executing while the previous step is still undergoing. We call that parallel combined with parent. And again, I apologize, I know I'm massively out of time. So I'm gonna stop there and we can take a quick look at Q&A, Monica, if you still have some time to stay on with me, or what I can do is I can follow up offline like we did last time for the Q&A, if you guys can send me the chat questions.
I think we can definitely go over time a little bit. If anyone needs to drop off, we will send you a link to the full recording today. You can stay on. We've got quite a few questions here for you, Maria.
All right, so let me take a quick look. So the usual questions, will this presentation be shared and available? Yes, all of the slides and the video recording will be made available. Okay, but we may intentionally join a small one-row fetch with a large table. Okay, I see more of a comment than a question. Seen join clause, but I've also seen how to use where clause predicates to do the join. Is one approach always better than the other? Okay, so I guess the question is, depending on how you write your SQL statements, depending on whether you use ANSI SQL or Oracle kind of default syntax, is whether you want to do the join, all the join information in the from clause, or do it as where clause predicates. Where you specify the join condition can sometimes determine the join order, but normally under the covers, Oracle, when you submit a query using ANSI syntax where the join is specified in the from clause, we'll often translate that or transform that query and rewrite it in Oracle SQL to give us all the different possible access methods and join methods. So it shouldn't really matter which way you write your queries. We should be able to get you the best execution plan possible, because we'll do that transformation or the rewrite from ANSI to Oracle to check all the different possible access and join methods and then pick the one with the lowest cost. So it really shouldn't matter which way you write your SQL statements. You should still get the best or the lowest cost plan. So the question is, what about a filter operator? It kind of operates like a nested loop, but it's not considered a join. What would it be considered? Filter predicates or filter operators are access predicates. So they're used as part of an access. So access predicates are where clause predicates are divided into two classes. We talked about this last week. We talked about access predicates, where the where clause is used to help us find the data we're interested in as part of the data access. So things like row ID and stuff like that are considered access predicates. A filter predicate, which is not used to actually find the data we're interested in, but it is applied after that data is found. Those where clause predicates are considered filter predicates, but it's overall part of the access rather than as a join. But you will see that information in the notes section underneath the plan. And if you go back to last week's recording, we started with actually access and filter predicates. So what is the top reason that an index is not used when you're expecting it to be used in a query? Chances are cardinality estimate is the #1 reason your index wasn't used, but there are other reasons for it. So so obviously cardinality estimate is the first one that I would look at, but join order is another reason why your index may not be used. So depending on the leading edge of your index, if we're coming to your table and after we've gone to other tables in the query, we will be looking to access that table through the join key and not necessarily through one of the where clause predicates or filter predicates you have on that table. So if your index doesn't start with the join key, then we may not select it. But cardinality estimates is the #1 reason. If it's a multi-table join, then it could be the join order. That's the reason why we're not picking the index that you're expecting us to. Cost is the other reason. So the cost of an index access followed by a table lookup by row ID versus a full scan of an index that has all of the columns we need in the table is another reason why you may not get the index you're expecting. We may pick a different index, and the reason for that is we can get all the columns we need from that index access rather than having to do the index access followed by a lookup of the table. So again, cardinality estimates, costing of those operations depending on how big the indexes are, etc., and how expensive it is to do the lookup by row ID of the necessary information from the table can also impact that. But cardinality estimates, #1 reason. Multiple indexes to choose from, as I said, so some are cheaper than others, and then the join order would be the other reason. So does Oracle have a partition advisor as part of the performance pack? We do. There is a partition advisor, but I'll give you my trick. So because it is part of the packs, I believe you do need to pay for it. It's an additional license. But I'll tell you the trick I use. If you have the ability to look at the workload, the common queries that are executed in your workload, and you can normally get that information either using StatsPack, our free tool, or using AWR if you've got access to those reports. Look at your top SQL statements, look at the where clause predicates and the join predicates in the queries, because if you start to look at them, you'll see a pattern. There's normally a set of columns that are being used. So it may be a date or a time column that's being used all the time in where clause predicates. There may be common join columns. So for example, the sales table is always joined to the customers table, or the orders table is always joined to the products table. Whatever those most common join and filter predicates are, they're the best candidates for partitioning, because it will maximize the partition pruning you may get. So if you don't have access to the NYOUG and tuning packs, and you're looking for the partition advisor, they're some of the key things you want to look for in your queries. So the question is, when does Oracle believe you should start partitioning tables? Like, is there a magical number of rows or volume of data? And it isn't as clean cut as that. The larger the object, the more benefit you'll get from partitioning it. But oftentimes I'll start knowing that a table is going to grow over time. You know, something like an orders table or a sales table is going to grow over time, even though right now the volume of data isn't very large. It may still be worth partitioning it. Typically though, we say if the individual partitions aren't going to be larger than double-digit megs. So in other words, if I'm subdividing the data so much that the individual partitions are less than 10, 20, 30 megs in size, it's not worth it. The overhead of having to switch in and out of these partitions is too much. So make sure the partitions are roughly sized, and I give guidance on that in the white paper, Best Practices for Implementing a Data Warehouse with the Oracle Database. We give guidance on those minimum sizes for partitions and subpartitions. So I recommend, Matt, that you take a look at that paper. Get better. Is there a negative? Okay, so the question is, normally parallelism is used to get better performance for a query, but is there a negative impact of parallelism, or can there be a negative impact? And there absolutely can. There is overhead when we do a query in parallel, because remember, we've got to do all that communication. The parallel server processes need to get allocated from the pool, and if they don't exist, they need to be created. Those processes need to be created. We then need to divide the work among those parallel server processes, and we need to do all of that communication to and from the different parallel server processes or groups, producers, consumers, the coordinator. All of that communication is overhead. Now, the reason why it's normally worth it is that the volume of data that we're scanning, filtering, and joining together is very large, and therefore we get a lot of benefit from parallelizing it. If the workload isn't that large, then the query would perform reasonably quickly in just a couple of seconds without parallelism, then the overhead of parallelism may be too much. So you're really looking to use parallel execution for queries where we're scanning, filtering, joining, aggregating large volumes of data. And so the overhead of this communication between the parallel server processes and the coordinator is actually worth it, because they're able to speed up the scanning and the joining and the aggregating of that data considerably. So yes, the longer running queries really see benefit from it. Short, very sub-second queries, the overhead of parallel execution isn't that great. So the question is about gathering stats. Slightly off topic, because the question is about system and dictionary statistics. So what are my advice about gathering system stats and dictionary stats? You definitely want to gather dictionary stats. In fact, starting in 12C onwards, the auto stats job does in fact gather dictionary stats for any object in the dictionary that's missing statistics. So it should, if you're using the auto stats job and you're using 12C onwards, then we're already doing the dictionary stats for you. because if we don't have dictionary stats, then the optimizer makes guesses rather than using dynamic sampling on the dictionary tables. And so we can really get some performing internal SQL from that. System stats is a tricky one. Some people have seen benefit from it in the past. My guidance and the guidance I got from the optimizer development team is do not gather them. Use the default set of system statistics that comes with the Oracle database, and because chances are for every query that you improve by gathering a new set of system stats, you'll break some other query. So just go with the defaults. It's far more consistent and the behavior is better. So dictionary stats, there's no problem with gathering those or letting Oracle automatically gather them for you if you've got the auto job enabled. But system stats, I would say no. So the next question is on how do you decide the parallel degree you want to use for your query? So for example, if your server's got 8 CPUs, what parallel degree would you use? Well, for me, because I understand the hashing algorithms that Oracle uses, and we often distribute the data among the parallel server processes, they send it, between the producers and the consumers using a parallel or a hash distribution. You want to make sure that because those algorithms are based on a power of 2, that your parallel degree inside the Oracle database is also based on a power of 2. So with 8 CPUs, you could probably do, depending on how much concurrent workloads, let's say we've got very few users and I want to speed up the queries as much as I can, I would use 8, 16, or 32 as my parallel degree with 8 CPUs. But if I had a lot of concurrent users, then I might even go with 2 or 4 as my parallel degree. Why? Because I want to make sure that I can have lots of users running in parallel, so I'd actually pick slightly lower, but always make sure it's a power of 2 for your parallel degree. Oh my goodness, there is still a lot of questions and we are 20 minutes over. So, okay, let me see. Let's go 2 more minutes and then I'll let everybody go. But as I said, we'll do our best to answer all of these questions offline as well. You know how I can avoid. Okay, so the question is sometimes, do you know, so I think the question is when they're trying to find the execution plan for a SQL statement, they are trying to find it in $V$ SQL plan, they're told that the SQL is not found or it's not there. And do we know a way to avoid that? The only way I know to avoid that is to increase the size of your shared pool. Sometimes this can happen if the cursor, the body of the cursor has been aged out, even though the statement is still executing. We have the execution, but not the full plan, not all of the operational information, because we've had to age it out to make space for something else. So normally I get that error message if I've got a space crunch on my shared pool. So one option, if you're seeing that, even though the statement is still running, the parts of the cursor have already been aged out, and that's what the problem is. Another question on ANSI SQL, is using ANSI SQL a bad idea? I think this is coming from the fact that in older releases of Oracle, we weren't very good at rewriting ANSI SQL into Oracle syntax, and therefore we wouldn't always find the best execution plan for ANSI SQL in Oracle. That really got overhauled and changed between 11 and 12.1. So we should now be able to do exactly the same optimizations, whether it's written in Oracle SQL or ANSI SQL. So as you move to the newer versions of the Oracle database, 12.1, 12.2, 18C, 19C, you really shouldn't see any performance difference whether you're going ANSI or Oracle syntax. All right, with that, I'm going to stop it there, but I really hope folks have found these 2 sessions useful. All of the slides that we used in the presentations, as well as the recordings, will be made available to you, either through the registration that you just used to register for this event, but I believe Coleman's also going to post them on the NYOUG website as well. So I really want to thank you all for staying so late this morning with me. I hope you found the session useful, and I look forward to talking to you all again soon in the future.
Thank you so much, Maria. Also, thank you, Coleman. And yes, like Maria said, everything will be made available to you. Someone from my team will reach out with today's session presentation and the recording. I think if you missed part 1, Coleman should have that on nyoug.org shortly as well. So definitely go check that out. And thank you all again so much for all of the time you've given us today. Thanks, Maria, for going over time with us too.
No worries. Thank you so much for putting up with me. I know I talk way too much.
Come back and speak again. Thank you.
Thanks, guys. Bye.
Here, everyone.